All right, recording is rolling. It is Wednesday, August 13th. All right, so main thing today is I want to throw a bunch of questions on the board. We'll have a PowerPoint put together just to get you guys thinking about things that you're going to eventually learn in this class. So some applications of physics, right? Yeah, try my best not to answer a bunch of these, but just throw them out there. And then as the class goes along, be learning cool stuff along the way. Okay. Now, today and most days I have a bunch of other uh, activities and ideas lined up too, but I'll run out of time at some point. So I do want to tell you guys what's going on next 2 days, Thursday, Friday, to round out the week. And right before that, also this right here, planner. Show hands. How many of you guys have a planner? Who has a planner? Spell. Okay, almost half the class looks like has a planner. All right. So yeah, guys, if you have your hands on a planner, definitely be using that planner. If you haven't so much yet, then yeah, just write some things in there. Just things you want to do tonight if you don't have any other assignments yet, right? And if you do not have a planner yet, then I do want you guys to go home and ask your parents to buy you a planner and start using that. So yeah, guarantee it will make your life much better. So be using a planner. All right, so Geneva Drive, that's this right here. Tell you guys a little bit about this. So next couple days, this is gonna be our project. Help you guys construct this and well, see what we do with this. I like to have this project at the beginning of the year for a number of reasons. Here, show you guys this in action. Okay, so you guys see my right hand, I'm continually turning this. My left hand, or this left gear is just turning incrementally. Okay, that's it. You're right. These pegs grab these teeth. Thank you. Okay, you guys see that? Okay. Sure. So, okay. Where do you think you might see one of these? Where could this be useful? Huh? And maybe like a clock. Ah, yeah, I'm thinking clock. Yeah, clock, like TikTok. Yeah, yeah, maybe some engines too. Yeah, there's probably a lot of applications you can do too, right? Right. Yeah, but if you have a bottle factory, you can go bloop, bloop, next, bloop, next, bloop. Right. How about those old time build projectors? Go back to mid 20th century. Guys, how do you take a continuous roll of film, like before the digital age, and turn it into like 30 frames per second? So you can put the film on one of these and you guys hear that clickety clack? It's one of these clicking. But yeah, clocks. Because if I say Geneva Drive, this might be from Geneva. Where's Geneva? What country? Switzerland? Yeah, yeah. And what are the Swiss known for making? Clocks. Ah, oh, okay, yeah, and some other things too. Yeah, chocolate too, but the physics answer is clocks. Yeah. Also, yeah. Matching this freeze works. So yeah, you guys get to work with your friends or your hands and think in 3D and yeah, how you gonna put this together. I mean, there's some math involved too. Like if you made these different sizes or you arrange the teeth differently, I bet you could get these to rotate different rates. And ooh, I bet there could be some physics science there. Okay. But here, show you guys a little bit underneath what's going on. So I got these pegs act as like an axle system. So it turns me like that. But I bet I want to put this one down first, put this one down after the fact. And so these teeth come from underneath to catch that. Yeah, so you guys get to think in 3D next couple of days, right? Plus, another thing it's good for is I know a bunch of schedule changes, so wait for a schedule to calm down a little bit. Right, so yeah, there's a bunch of good reasons for a project like that. All right, but main thing today, get you guys some physics questions here. Physics questions. All right. All right. All right, so these are approximately in order. You guys gonna see these in the class. If you see any reference to AP, don't worry about AP so much. But so how can you measure and quantify your observations, right? Especially historically, like where did any of this measurement stuff come from and scientific method? Like what did happen in history that led to this point where we're all sitting on this classroom on the second floor and right, you guys are reading questions off a PowerPoint slide and it's useful to society because the government's paying for me to be here, and well, I guess by law you have to be here. So let's see, well, thousands of years ago, because what were people doing? Say like 50,000 years ago, what was everybody doing? Surviving. Yeah, surviving, yeah, hunting and gathering, right? You'd run around on the savannah somewhere, right? And I don't know what people could count to back then. Maybe I don't know, 10 or 20 or something. I don't know what people could count to, but probably not their met, right? And then years roll by, and there's an agricultural revolution and different developments, and people need to have more complex counting systems. And okay, we get this Roman numeral method. which is okay for counting things up to maybe a couple thousand or something, right? Okay, now they can put armies together and they order blocks and build an aqueduct or something, right? But guys, Roman numerals, can you do high level math like algebra and calculus with Roman numerals? Not so much, right? Maybe you can do some basic counting. Right? Okay, then we get like place value systems and then more hard science. And we think, okay, what kinds of things do you want to measure? Right? Then start looking around. Well, I can measure, say, the width of the door. Okay, so some kind of length. Okay, I can measure maybe how heavy is something. Okay? How many things are out there to measure, right? And is there some standardization of units and where would that have come from? So look back thousands of years ago. It's like, how do you construct this table? Oh, okay, well, it's got to be like 20 palm lengths wide, 20 palm lengths. Okay, but everybody has different palm length, or if there's some standard, maybe it's some local standard, and go to the next town, you don't know what anybody's talking about. And so, what about in this class that we're going to almost exclusively use the metric system, right? So, where did like 1 meter come from? Where did 1 kilogram come from? Right? There's a story behind all these. Right? Probably across a river. The river flows downstream. How can you determine your speed and direction relative to the shore? Right now, that phrase right there, speed and direction, that's in physics what we're going to call velocity. So when I say velocity, it really implies both those things, a speed, but also direction. Sometimes directions implied like forward or upward or something. Right? But here's what we got. Maybe we got a river flowing like west to east, and you're trying to cross it in your boat going south to north. Right? Now, if your boat's aimed straight north and the river's flowing like, east at the same time, right? Suppose there's a monkey sitting in a tree on the shore, and the monkey's watching you like paddle and being swept down shore at the same time. The monkey points a radar gun at you. Does that radar gun capture maybe something to do with your paddling, but also something to do with the river current? Right. And what direction would you be going? How's that connect? The speed of a car, distance to the next town. Can you calculate the time to reach the next town? Actually, this one you guys probably know already. Suppose you're driving on I-95, you're going straight north. Jacksonville is 140 miles away. 140 miles. They're going 70 miles an hour. How long does it take you to get there? About 2 hours, you think? Okay, because 70 times 2, 140, right? Like that. All right. All right. Vector. Ooh, let's give this vector method. So plane engines are running. Now, guys, the plane engines, are those plane engines pushing against the surrounding air? Yeah, the surrounding air. Right. But maybe there's somebody down on the ground looking straight up at the plane. They point a radar gun at the plane. Right? Now, does the radar gun reading on the plane, which is relative to the ground now, right, is that the same as the plane relative to the air? Right. Well, it would be if there's no wind, right? If the air is just still. But what if there is wind? Right? What if you have a always forget which one's the tailwind, which one's the headwind, right? What if the plane's getting a boost? Ooh, now is the plane going really fast relative to the ground? Right? Okay, so now we're starting to think in terms of vectors. Right? So here's the plane relative to the air. Here's the air relative to the ground. Do you think you can put those two together and create the plane going relative to the ground? Which is a different concept, right? Right? What if the plane's fighting the wind? Do you guys think now the plane's crawling really slow relative to the ground? And here's your dark green resultant right there. So dark green resultant, dark green resultant. Okay, plane to air, air to ground. Therefore, here's the plane relative to the ground. Okay. What if you have a crosswind? Crosswind. And the plane's pointed maybe straight north, but does it move straight north? Right. And also how fast. Right. So what's the direction it's going, but also how fast it's going. So got somebody down on the ground pointing a radar gun up at the plane. How does that compare to, say, the instrumentation on the plane, which is relative to the air? Would that be? I gave you guys a bunch of thumbnails a couple days back. And some of these are updated a bit, so this may not look exactly 100% same as on the. Okay, so I did some copy and pasted from some past presentations, but all these silver banners are related to either scientific method or measurement, one way or another. All right, we're gonna more slowly go over these in the coming couple weeks. All right, so once we get that down, so how do you measure things? How do you quantify things? Some basic vectors, trigonometry. We'll do some sine and cosine. Right. An early topic is going to be kinematic motion, which involves linear motion. So just how do things move? Right. Here's a classic question. Can you feel the speed of a car while you're sitting in the passenger seat blindfolded? Right. So guys, your friend's driving a car. You're in the passenger seat. You're blindfolded. Can you feel like, oh, it feels like we're going about 45 miles an hour? Is that a thing? Can you feel that? Right. But are you on a giant spinning earth going almost 1,000 miles an hour straight east right now? Can you feel that? Right. You feel something in the car. Right. And what would that be? And how do you quantify it? All right. I'll have you guys do this in a few weeks. How do you guys pair it up? One of you has a ruler, drops the ruler, the friend catches it fast as they can. Right. Now, uh, do you think there's a maybe some delay between what's happening in the world and your brain being able to process it, right? So deer steps out in front of the car, takes you a tiny fraction of a second to, ooh, I better slam on the brake, right? And even more time after that for the car to slow down to stop after that, right? So what is that delay? What's the delay between, say, the sound waves from my voice hitting your ears, your brain being able to process that? Because it might feel instantaneous, but it isn't, right? And when we hit this day right here, you guys are going to find out. Do you guys think the longer the delay is, the more the ruler will have fallen? Right? Right. But what is that relationship? Right? And here, I'll spoil this a little bit, not too much, right? Yeah, I'll tell you guys that's not a linear relationship. And what I mean by that is if the ruler has fallen twice as far, that does not correspond to twice the amount of time. Right? So suppose you catch it at 10 centimeters and your friend catches it at 20 centimeters. So 10 versus 20. Right? So the ruler will have fallen twice as far, right? But that's not twice the time. It's something a little bit different. So how do things fall? Huh. Right. So eventually it's going to lead to helping answer something like this projectile question. If you blast a cannonball horizontally off a cliff and spot where it lands, can you determine the blast speed of the cannonball? No. So, well, we won't be using cannonballs, but how about soft little squishy bouncy balls? Right? I have some launchers. We're gonna take these out to the balcony a few weeks from now. Have you guys launch some squishy bouncy balls? Right? And ooh, do you think you could take a meter stick and very easily maybe walk up the stairs and okay, measure the height of this balcony right here? Can you do that? Right? And then spot where the ball lands, and then take either a meter stick or a trundle wheel and measure how far out does the ball land? Right? Do you think that there's enough information there, like in principle, where you can back calculate what was the blast speed, like how fast was that bouncy ball fired? Can you figure that out? Right? How about this? What else could maybe be a variable that was sort of implied in all that? What if you take this whole system, like the exact same launcher, exact same ball, exact same cliff height, except on the moon? And on the moon, there's gravity. It's just really weak gravity. It's not as much gravity, right? So on the moon, with the same launcher and the same ball and the same cliff height, do you think the ball would land really close to the cliff or the same place or would land really far away from the cliff? Yeah. And what equations could link this together? Okay. So part of this has something to do with the strength of the gravity field, which is probably somehow related to this ruler dropping also, isn't it? Huh. Huh. That's I wonder how could you quantify it? How strong is Earth's gravity field? Ooh. Okay. About this one. You're in a ball throwing contest with your friends. Who can throw the baseball the furthest across the field? Now, you can only throw as fast as you can throw, so you can't really change that so much. Okay? What you can affect is the angle you throw the ball. So maybe you throw it 0 degrees relative to the horizontal. Doesn't go very far. Hits the ground, right? Up this to 10, 20, 30 degrees. What if you throw it 90 degrees to the horizontal? That's to say straight vertical, straight up. Right? Does it pretty much land exactly where you threw it? Call it zero displacement, so it hasn't really gone anywhere from start to end. Okay. Okay. And again, back to the question, then it's like, what angle would you have to throw it at to maximize this horizontal displacement right here? Right? And what math could back that up? Ooh. All these red banners related to these, and some of these might be updated a little bit, but what we got here. I like to a lot of times give you guys, so every color banner is basically a different section, right? Give you guys a list of units, variables and units, so you know what to work with. Okay, we've got some classic equations here. I see a bunch of graphs to a bunch of different scenarios. Here's a reaction time for dropping a ruler, how to solve that to be getting into. Here's some projectiles down here in the bottom right. Here's your labs, right? How about take a bathroom scale in an elevator? Right? You guys ever step in an elevator, the doors close, and the elevator starts to move? Can you feel that? The elevator starting to move? Okay, yeah, feel a little bit. Whoa, it feels the floor moves, right? Right. But then during the main motion of the elevator, it's supposed to take like 10 seconds to reach the destination floor. Does it basically feel like just sitting in your desk right now? Yeah, I bet it does, right? But what about coming to a stop? Can you feel the elevator slowing to a stop? Yeah. Right. In fact, if you're going up to a destination floor or down to a destination floor, I bet you'd be able to feel the difference too. Like if you're blindfolded and your friend saying, "Are we going up right?" But again, maybe as the elevator is starting to move and coming to a stop, right? Suppose you bring this scale along with you and you're watching this needle move around. Do you think that needle's going to jump around a little bit as the elevator's like changing its motion? Right. And what could that tell you about the motion of the elevator? Like if you know what your normal weight is, just standing on a sidewalk, right? You watch that needle like jump up or jump down, right? What could that tell you about the motion of the elevator? Okay. Ooh, you're engineering a truss bridge. I got like a truss arch looking bridge right here. How can you determine the tension or compression in any part of this bridge, right? Like this component right here, right? Is this in tension or compression, and how much, right? Because that could be good to know for a number of reasons, right? So suppose there's a county that wants to build a bridge over a little river like that, right? And how this normally works is, okay, so if you're working for the government, say the county government, uh, they will normally put out a bid for contracts, right? And then they normally, how it works in the American system is just pick the lowest bid. So who can accomplish what we want to accomplish, right? We want to build a bridge that has these specifications, can handle this many cars, might last like 50 years, right? Who can do that for the lowest cost, right? Right. So on your side as an engineer, you have to, okay, well, what do I want to build this bridge out of? Okay, well, if I know that this component here would be, say, in tension or compression, and by how much, right? I can, and I know what materials I'm going to make it out of, right? Say I want to build this out of steel. I can know what the strength the steel is. Therefore, I can know what does the cross-sectional area have to be so it can match the specifications, right? And what this bridge should probably be like equally strong or equally weak throughout, depending on your perspective. It's glass half full, half empty kind of, right? Because if it's super strong on one side, then what that might indicate to me is maybe I overbuilt that, I over-engineered that, and now we're just spending extra money on like too much steel that we don't really need because it's too strong, right? So yeah, considerations, right? How about this? If there was a component that was in tension, would you want to use steel or concrete? Right? Like concrete, you can build big old skyscrapers with concrete, right? Concrete is really strong compressive strength. Right? But what if you pull on concrete, like tensile? Does it pop apart relatively easy? I mean, probably a situation like that would, right? So anything in tension, I would definitely not want to have concrete going on, but steel's okay though, right? Uh, there was a whole class I took in college that was just called statics, and it's just solving puzzles like this, right? Figure out what's the tension or compression in any part of a structure like that. Okay. Ooh, something I have you guys do a couple months from now. How much friction is there between two surfaces? Can you predict the tilt angle of a desk so before the top object might slide off? So I take some object, put it on a desk. Your desks are kind of slick, right? What if you tilt the desk like 3 degrees, 4 degrees, 5 degrees, and the object stays on? Right? Uh, what about 10 degrees? What about 15 degrees? What about 20 degrees? I bet at some point it's going to break friction and start sliding off. Right? What if you put down wax paper first? Really slick, hardly any friction. Wax paper. Do you think maybe a really shallow angle it will start to slip down? Right? What if you put down sandpaper? Right? Really coarse sandpaper. You think you could probably tip it to a higher angle? Okay, so it's something to do with material properties here. There's some way you can define like what's the friction between surfaces has something to do with the materials. Okay? Has something to do with the angle you can tip it, right? And maybe some other things too. Right? This might be part of a larger lab. Right? That okay, yeah, ignore all the AP stuff, doesn't matter, right? Some of these slides I probably need to rearrange anyway too. So anyway, how much fuel does it take Voyager 1 to keep going? Right, so there were a couple of spacecraft launched in the 1970s, Voyager 1, Voyager 2. And they're exiting our solar system now. They're like at the edge and they're just going. They've just been going for decades. Right? They're just going. Right? How much fuel does the Earth take to keep going around the sun? Is it just going? It's just going. It's been going for billions of years. Just going. About four some billion years. Uh, what's the longest drinking straw that could possibly work on, or how do these straws work at all? And what would the some kind of limiting factor be? Um, are we in an atmospheric pressure right now? We're definitely not in the vacuum of space. Okay? Okay, stick a straw in a glass of water, draw the water. Okay, not too hard, right? But what if you did that on the moon? What if you had a glass of water on the moon where there is no atmosphere? I mean, the moon doesn't have an atmosphere. It's basically vacuum, right? Would a straw even work on the moon? I don't think it would, right? And if you bring this back to Earth, okay, well, we are in some finite pressure. How much pressure? How could you quantify that? And how could that answer a question like this? Back hundreds of years ago, there might be towns on some hilltop, and there was a lake down below, and they had to pump up the water, right, to get the water from the lake to the town. Right? But they would figure out pretty fast, oh, there's only so far we can actually pump up the water. Kind of runs out. Huh. Uh, oh, Here's the Earth and the Moon to scale. Like if you zoom way back and telescope down on the system, that might be what the Earth and the Moon look like from a distance. Okay. Guys, is the Earth pulling on the Moon? Yeah, it has something to do with keeping it in orbit, right? Uh, does the Moon pull on the Earth? Oh wait, isn't that where tides come from? Tides, right? Got two high tides, low tides every day. Right. But which is a greater force? What does that say about the fundamental laws of the universe? What would happen to your weight? So let's take that bathroom scale from the elevator a few slides ago. If you started to tunnel down to the center of the Earth, ooh, right? So you're on the surface, you weigh, well, I don't know, 100 pounds or something, right? You start digging down. You go down like 100 miles, you weigh yourself, and then another 100 miles, you weigh yourself, another 100 miles. Right. What would you weigh at the center? Yeah, ignoring the molten whatever, blah, 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 right? Just as a gravitational exercise. Right? What if you take off, or what if you had an extremely tall building, maybe like a, what do they call that? If, I'm thinking like a space elevator, it's like futuristic sci-fi. Right? What if you had like a building that went all the way to like the moon or something crazy, right? Okay, you like climb that building. What would happen to your weight as you're standing at like different heights one way up there? Oh, actually, that segues to this one right here. You guys ever seen satellites fly by overhead? Seen satellites? Yeah, watch the night sky. Oh, tonight you might see some shooting stars. You know, we're in the middle of a meteor shower. Yeah, sometimes we'll see a satellite go by. It looks like a little star, and just like constant velocity just goes across the sky. Looks like. Um, if you're ever out west where there's no light pollution, you guys ever been out west where there's no light pollution? Yeah, okay. Guys, watch the night sky. You'll see satellites all over the place. It's like almost continuous. It's crazy how many are up there. Now, of course, we're in the suburbs in Florida, so there's enough light pollution where you don't really see them very often, but they're there. And one of them is the International Space Station. Does anybody know? Bet somebody knows. How long does it take for the International Space Station to orbit the Earth once? You may know.
Couple hours.
Yeah, it's like 90 minutes. Yeah, 90 minutes. Right. 90 minutes. Right. How long does it take the Earth to rotate once? About it's like 24 hours, right? It's 24. Okay, right. So you guys know that. How about how far up are those satellites though, including the International Space Station? Right. Now there are different orbital levels, but one's called low Earth orbit. It's about 400 or so kilometers up, plus minus a little bit. Right, so the International Space Station is like right in there, 400 kilometers. Right? Guys, let's look at this building right here. What building is this? Aha, Burj Khalifa. Yeah, I think it's the tallest building in the world. Right. Now, this is not even 1 kilometer tall. Right? So let's make believe, though, that there was a tower that went all the way up to low Earth orbit, like 400 kilometers tall. So like hundreds of times what this building is even. Right? And you go all the way to the top floor of this 400 kilometer tall building. And you look out the window. You see, see her fly by in the International Space Station. Right? Now, those astronauts inside the space station, how heavy do they feel? They feel weightless? Yeah, feel weightless, right? That's may call that apparent weightlessness, right? Okay. How heavy do you think you would feel at the top of that 400-kilometer tall building? Okay. Well, I will sort of spoil this one a little bit. Turns out you would have about 90% of your weight that you do down here at the surface of Earth. So if you weigh 100 pounds here at the surface, and we've all lived our entire lives really here at the surface, if you weigh 100 pounds here, if you climb a 400-kilometer tall building, you weigh approximately 90%, right? And you look out the window and you see her fly by and she feels weightless. Huh? How does that work? All right, so all these orange banners are related to well, forces. I got Newton's laws. Actually, that slide we just did, I should put later because it's related to the rotational stuff, right? But okay, but some of these, some different force slides. Okay. Ooh, fun bus time. So what angle would you have to bank a road going around a curve so that drivers would be able to make the turn, even when the road is iced over? Because yeah, if the road's iced over, you don't get a lot of help from friction, right? You guys have your driver's licenses by about now? About right? You guys been on the interstate, right? And then you hit the off ramp, so you're going from 70 miles an hour down to and then you have to slow down real fast, like 30 or 40 or something like that, miles per hour, right? You're going around a curve a lot of times, right? Well, those off ramps, right? Do they usually bank the roads a bit? Bank the roads? Yeah, and that'll help you out too, because you can definitely feel it. You're like, okay, well, if I was going too fast, like if I was keeping my speed at so many miles an hour, right? And or this road's curved too tightly and or it's not banked very well or not enough, you think your car might be flipping off the road, flipping off that off ramp. Okay. How about back to here? What if you're getting no help from friction at all? Do you think there's some amount you could bank this road? Suppose it's up north, it's the winter, and we're expecting there to be ice in the road sometimes, right? And you want this traffic to flow at, oh, I don't know, like 40 miles an hour, right? Do you think there's like some angle you could bank the road where you could keep the cars basically on the road? Right. Now, I wonder what does that have to do with maybe the radius of curvature that's going around? Huh. There's some physics equation there. Right? Hey, vertical loop in a roller coaster. How fast does a roller coaster or cart have to go vertical loop to stay on the track? Or, I mean, realistically, they probably have some safety feature. It doesn't actually fall off. But what about this guy here? What if this guy's not wearing a seatbelt? Right. Now, if this whole thing actually did come to a stop, this guy's not wearing a seatbelt, what happens? Yeah, he gets his own special kind of ride. But what if this is in motion? It's going fast enough. Ooh, could this guy get all the way around even not wearing a seatbelt? He can get around if it's going fast enough, right? Right? Yeah, and what speed would that have to be? Uh, it might have something to do with, again, like the radius of curvature. Do you guys think, you guys see I'm tracing out basically a circle? I'm trying to fit a circle flush to this roller coaster right here. The circle, right? Maybe something to do with the radius of the circle that could be flush to that curve right there. Do you think it has something possibly also to do with the strength of Earth's gravity field? Like if you took this whole system to Mars or the moon, let's go to the moon. There's really weak gravity. Do you think you could make that turn, that loop around on the moon very, very slowly and it still stays on the track? Yeah, probably the necessary speed would be not as fast, I think. Right? Right. Wonder what these equations are, right? How all these variables link, this radius of curvature, the strength of the gravity field, right? I wonder if the weight or the mass of any of these people has anything to do with it. Maybe, maybe not. Right? Sometimes variables cancel out in physics. You find out, right? Um, yeah, okay. You guys kind of thought about this one a few slides ago. How fast does a satellite have to go to say an orbit? Call it orbital speed. How fast does a rocket have to go to turn off its engines and still fly away from Earth's gravity? Maybe all the way to the moon if you like. Right? I'll call that escape speed. Ooh, so orbital speed, and this could be escape speed. Huh. Right. How could you figure those out? Okay. Okay. So these are circular motion and rotational type. Right. So, there's purple ones, there's gold ones for different reasons, but okay. So I'll kind of go together here. Right. So I think it's rotational type. Right. Also, okay, here's more gold banners that are more related to gravitation type questions. Right. Here's universal gravitation. How much does the Earth and the Moon pull on each other? For that, right? Oh, hey, here's this vertical loop question we were just looking at. Right? Oh, here's orbital speed. Right? Now, escape speed. I think on your guys' prints, I actually change this one to green for it. Actually comes out of energies. How you can drive this one, but yeah, got tides going on. Ooh, okay. Here's a classic energy chapter question in physics: is you slam on the brakes in a car. How much road does it take to brake to stop? Right, so you're driving along, right? You see this boost step out in front. It may take some time just for reaction time. You guys remember like dropping a roller, some reaction time just to know to press the brake, right? And then the car itself brakes to stop after that, right? What's the relationship between car speed and braking distance? Hint, not a linear relationship. I'll tell you what I mean by that. Is it that if the car is going twice as fast, turns out it does not take twice the amount of road to come to a stop, right? Suppose you have a car going 30 miles an hour next to a car going 60 miles an hour. They both slam on the brake at the same point in the road, right? Now, do you think those two cars take the same amount of road to brake to a stop? Or how many of you guys think the car that's going faster takes more road to come to a stop? Yeah, turns out it does, right? So 60 miles an hour versus 30 miles an hour, yeah, it's going to take more road to come to a stop, right? But it turns out it actually is not twice the amount of road. It's actually more than that. I'll tell you guys that too. More than that, right? But we'll put those into equations. Well, a few months from now, you guys get to learn that too. Right? Ooh, I have a pulley system here. I have a fancier version actually built in class. This one on the PowerPoint side's a little bit old. Right? You guys see that trellis over there? That trellis over there. Right? But it's the same principle. Do you guys see here? I have this big old 1 kilogram mass. Right? Which has a weight. Now, mass is like how much material, how much inertia. Weight is like a downward gravity force. So talk about those two. You have a concept there. But this weighs 9.8 newtons. I'll usually just call it 10 newtons. It's like a 10 Newton weight right here, right? Right, and we've got some fancy strings going on. And what about the other end here? On the other end is, oh, look at that. It's a little 2 Newton weight, little 2 Newton guy. Right? And there's a spring scale here so you can measure what are the forces on either end of this. Right? So here's your question. How can you amplify your physical strength? That's to say, get a mechanical advantage with a pulley system, which is one example of, it's called a simple machine. Yeah, right. So you can amplify your strength. So if you're a little weak guy, I can only pick up 2 newtons. That's all my strength. Oh, my muscle, I can take 2 newtons. Right. But if you have one of these lying around, you attach something that's 10 newtons. You're like, I'm super strong now. Pick up someone's 10 newtons. Ooh. How do you do it? So yeah, a few weeks from now, you guys will be constructing some of these pulley systems. Have you ever seen water flow uphill? Have you seen balls roll uphill, water flow uphill? And if not, I wonder if there's some physics principle for why that might be. And if you did, like, I wonder what might lead to an exception, or I wonder how maybe that could still be consistent with laws of nature. How about perpetual motion machines? Now nobody's built one of these, but why? Why does that not work? Look back at, say, Leonardo da Vinci sketches. He was trying to create some of these. How about here's what this might be related to is how about all the energy being used in this room right now? So power and projection, power and the air conditioning, lights. Okay. So any energy that's coming from the electric grid, but that's being continuously, the energy there is constantly being put on the grid, and that's coming from like mostly fossil fuels, about 20% nuclear. Okay? So somebody with like burning coal or running a nuclear process, boiling water, turning a turbine, you push a magnet past the wire, and that transfers the energy onto the grid. Okay, so that's how you get energy from coal, from nuclear, and you're able to run everything in this room from the grid. Okay? But you know what would be really nice is if we didn't need the coal at all. Like, wouldn't it be really awesome if you could just have a bunch of ball bearings like that and some spokes and wire it up in such a way that it just like continuously rolls, right? You could get a turbine that way. But no one's ever been able to do that, and never will. Okay, what's the physics principle behind that? And how can you take the physics principle behind something like that and solve a bunch of physics puzzles? Right? Oh, here's a car braking to a stop. Right, ooh, we've got Galileo dropping balls off the tower here. Yeah. So all these green banners are related to in physics. The concept is energy, conservation of energy. Right. How can you determine the firing speed of a bullet by firing the bullet into? Oh, yeah. Oops, I don't actually have a picture for this. Oops, I missed that. But say it's the year 1880, and you have the new pistol, new revolver. How fast can this pistol fire? How can you figure that out in 1880? So what they would do is they would measure the mass of the bullet, and they have a block, measure the mass of the block. Right, put the block on a pendulum. Firing the bullet into the block, it's going to swing up like a pendulum to some height. Now, if you know the mass of the bullet, the mass of the block, and the height change, there is enough information there. You can go through collision physics and figure out what was the firing speed of the bullet. Okay, so have you guys solved that in time? Can a bouncy ball return higher than it was dropped? You buy the world's bounciest bouncy ball, you drop it from 1 meter. How high could that bounce up to? Okay. What if you have a half-deflated tennis ball? Is that it'll bounce a little bit, but not very well? Okay. What if you have a ball of clay? Stick to the floor. Okay. Do you think there's some way you can quantify how bouncy is something, right? What would be the term for that? What would be the units for that? How bouncy is something, right? Once a billiard ball has been set into motion, is everything that results in the next 5 to 10 seconds basically determinable, right? So you strike the cue ball, all the other balls are sitting on the table, all in that plane, right? You know masses of those balls, you know how bouncy these balls are, right? And if you played lots and lots of billiards, maybe you get it intuitively. Of course, in this class, maybe solve it more with math, right? On paper, right? So you strike the cue ball. How can you know the 7 ball is going to go into the corner pocket? Right? Is that determinable at that point? Right? This has some crazy implications too. If this is determinable, like once you set the first ball in motion, everything's about to happen. It's like, okay, it's just fate at that point, right? How far can you extend this analogy, right? Like for example, where do your thoughts come from? Like how do thoughts enter your mind, or how do you decide what thoughts to act on and make decisions, right? Is that all happening inside your brain, right? Is your brain made out of a bunch of little particles? So is this determinable, right? And this is one of the big questions in history and philosophy too. is how much is fate, right, versus how much is free will, right? Ooh, so all these blue banners, you guys have some updates, so you guys have some extra ones that aren't even on here. Right? But yeah, so anything collision physics is related to momentum, impulse. In a few months, I think we're about to have Winter Olympics. Right? You guys ever watch figure skaters? So say they have their arms out and go into a slow spin and then pull their arms in. What happens to their spin rate? Yeah, spin faster. What's the physics principle there? Right. Wonder how much work, how much energy it takes to pull your arms in at the same time to make that happen. Huh. Ooh, equilibrium. So say we're interested in the tensions in these ropes right here. What are the tensions in the scaffolding ropes? Right. So I've got a couple of friends on the scaffold. It's being held up just by a couple of ropes there. Right. He said, hey, walk over here. Walk over here, closer to me. But okay, starts walking over closer. He starts clanging this rope on the left side. Boing, 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 boing. Okay, now walk back over to your side. So okay, walks back over to the right. Pluck this. Boing, 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 boing. Ooh, what's happened to the tension here? And what's happened to the tension in this one at the same time, do you think? Huh. Huh. I wonder what the rules are. What does that have to do with the weights of these two guys? What does that have to do with the positions of where they're standing? Because as they're walking back and forth, those tensions are changing. Huh. I bet you could rig that up and do a lab on that. Right? Maybe throw some spring scales on there, some lab weights. Right? Ooh. You guys see there's a big old hurricane in the Atlantic? Okay. Now it looks like it's gonna curve north and miss us, but hey, we might get a hurricane this year. Okay. You guys ever notice every single hurricane that passes over Florida always spins which way? From above. Counterclockwise. Yeah, sure does. Huh. Why would that be? So plant some ideas here. What if you go to the eye of this hurricane? Now, in the eye, is that going to be a high pressure or a low pressure system? Hmm. Yeah, low pressure. Yeah, turns out it is. It is low pressure. Yeah. Now, if you have a low pressure system in the eye, is that going to vacuum uh, the surrounding air mass to it? Right? Is that what low pressure does? Like vacuums, right? Right. Now, combine that with the fact that you're on a giant spinning ball, right? And when those air currents are changing latitude, there's a discrepancy between their what's called linear motion and angular motion, or it's their linear velocity and their angular velocity. And that will set up these counterclockwise systems, right? Unless you go to Australia, is what if Australia is hit by a cyclone? Which way is that going to be rotating? Yeah, clockwise. Yeah, across the equator, and the physics reverses. Look at that. Right. Ooh, you guys ever tried to balance? Got a couple of tightrope walkers here, but maybe you try to balance on a log or something like that, right? You're walking along. You guys do like they're doing like hold your arms out like this, hold your arms out. Or again, you got someone with a pole right there. Got that right picture. Got a big old pole. Right? Does that help you balance? You hold your arms out? Yeah. Yeah, sure does. Right. But what's the physics? Like, what are you physically changing? Are you changing your weight? No. Are you changing the location of your center of mass? Not really. Still kind of averages out to the center. Okay. But you're changing something though. Okay. Another example for you guys. Got to switch my screen over here. It's related to that. How about you guys ever tried to balance a pen on your finger? Balance a pen? Can I do that? But I can't. It's like nearly impossible. It's pretty much impossible to do that. But how about this? Can you guys take a big old meter stick, balance this big old meter stick right here? Balance that? Yeah, you do that. There. These are off camera. Okay. Yeah, look at that. You do this for a long time. You know what? Well, I got these out. This kilogram mass and this meter stick, these are base units for, mass and length. Okay. I'm going to pass this around class so you guys can get your hands on these, kind of feel these. You know, the idea of what is 1 kilogram, what is 1 meter. Yeah, so you guys can pass those around. But yeah, why is it then? And what does that have to do with these over here? And so, something to do with like if you spread your mass out, you have more stability. What's that up? Ooh, let's have a roll race. Roll race. Who's gonna win that race down the incline? So I got a bowling ball, a basketball, a solid cylinder, and a ring. Okay. Let's say there's a little bit of bit of friction, so it induces rolling. So they start rolling down the incline. Okay. So do you think all four of those are going to tie, or do you think they're going to rank like first, second, third, fourth? Yeah, they're going to rank somehow. Somebody's going to win, and somebody's going to lose that race. Now, I'll give you guys a little hint here, or a little tidbit. Turns out in the math, and also, well, in real life too. We can try this out. Okay. Uh, the individual masses and also the radial sizes end up canceling out in the equations. So it doesn't matter. Like the bowling ball is way heavier than the basketball. It ends up not mattering in the end, right? What does matter is the distribution of the mass. So the fact that the bowling ball is solid all the way through versus, guys, the basketball is all the mass pretty much on the surface, the surface of the sphere. Yeah, and that's the critical difference that ends up, well, mattering to the solution. Like who wins this race? So how's the mass distributed? Okay. Purple banners. I think you guys have a couple of pages of purple banners, right? Or all these rotational dynamics. What's going on? Okay. Ooh, you guys ever dive into a pool? Deeper you go, you guys feel that pressure increasing? Right? Oh, so what does the pressure have to do with how deep are you in a pool? Um, and it turns out pressure doesn't just have to do with how deep. It's also related to, well, if that fluid is in motion, if water's in motion, that can change the pressure too. Okay. So speaking of which, let's look at a pipe system. How do the speed and pressure of water change through a pipe system of various diameter pipes? Suppose you have a large pipe leading into a small pipe. Right? What's the principle there? Like what's conserved? What increases? What decreases in terms of speed, pressure? What if you were a fish swimming around inside the pipe system? Huh? You think you'd feel all the pressure changing? Right? I mean, I think in general, as you go deeper, that would be an increase in pressure, right? But also something to do with the speed of the water, which would also change with different pipe diameters. How would that affect things? Oh, Bernoulli principle. Ooh, how about this guy? Hey, we're back to a really weak guy trying to lift something really heavy. Ooh, maybe get a mechanical advantage out of a hydraulic lift. Ooh, right? Kind of like that pulley system, right? Same idea, just with fluids going on here. Hydraulic lift. Okay. So all these orange banners are related to, well, most of these are related to fluid dynamics. Okay. There are a few solid engineering ones. Got some bridge types down here, got stress and strain, but yeah, a lot of these are fluids like Archimedes, Pascal, Bernoulli, constant flow. Yeah, stuff. Ooh, what if this probably be pretty well into next semester. What if you have a spring, you hang the spring vertically, and you just attach a lab weight right here, right? And then you drop it and let it go. And it overshoots the equilibrium, goes to some maximum stretch position way down here. It oscillates back and forth for a while. Boing, boing, boing. Okay. Do you think it takes some amount of time to oscillate once, some amount of time? Do you think that amount of time has something to do with how stiff the spring is? How much lab weight did you put on it? How much mass? I wonder if it has something to do with the gravity field of the planet, or maybe not. Maybe you take this to the moon and it oscillates the same. I don't know. We'll find out. Okay. And then eventually this comes to equilibrium. So after like a couple of minutes, go wow, 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 and it comes to a stop. Okay. How does that equilibrium stretch position compare to that maximum stretch position? And what equations could back that up? And then of course you try this out in real life one day with a lab and see how it's compared. Oh yeah, it all lines up. Uh, oh, okay. So all these gold banners are oscillation. I think you guys have another. Oh, okay. You guys have another set of gold banners for waves. Well, okay. There's more than just one page of gold banners, but anyway. How about this? You guys stand by the sidewalk, car goes by. Hear that pitch shift as the car goes by. But you don't hear that if you're in the car. You only hear that if you're standing on the sidewalk. Guys, what's that called? What effect is that? Doppler effect. Aha, Doppler effect. Okay. If you heard those pitch shifts, could that tell you something about how fast the car's going? Or vice versa. You know how fast the car's going. Can you predict what the pitch shift's going to be? Ooh, here's a light version of this. You guys know if you look at distant galaxies, almost all the other galaxies are moving away from the Milky Way galaxy. Tells something about the expansion of the universe. That's also a version of the Doppler effect too. We'll do some electric circuits. I'll show you guys how circuits work, flashlights. If you hook up a battery, this could be a battery right here. These lines could represent a battery. Here you have a light bulb, right? How does current flow? What does that do with the voltage of the battery that you pop in? What does that do with the resistance of the bulb that's in there? Okay. We'll look at systems with the series and parallel resistors. Okay. And then what if you hook magnets up to this? Okay, so what if you have either a battery next to a magnet? There's a little magnet hidden down here, right? Or vice versa. What if you force a wire past a magnet? You can generate electricity here, or here get electricity flowing, create a basic motor. A lot of you guys construct a motor basically out of like a battery, a magnet, and a wire. So that'll be near the end of next semester. Okay. So how's electricity generated? How can you build motors? What's it got here? Yeah, I have an extra slide for some other physics we'll do. Now this is its own slide just because all these topics right here are not on, well, these are not on the AP exam, which I get, no, you guys are not taking, but just for my AP class. Okay, say, okay, not so much. Right. But yeah, you guys ever had a friend step in the pool? It's like, hey, what happened to your legs? They're super short. It's like, oh, well, not really. It's just an optical illusion, right? Something like this. Called Snell's law. What causes that refraction? What can you do with that, right? If anybody's wearing eyeglasses or contact lenses, ooh, I bet there's some physics going on that has to do with to fix your prescription. We'll do a little bit of engineering. Might have you guys construct a toothpick bridge at some point. Engineering, laws of thermodynamics, like how efficient can a machine be, right? Why do certain processes only work in one way? How can you quantify that? Okay? The theory of relativity. That's sort of like Einstein physics. Right? Uh, Tidbit here. It turns out that the GPS in your phone, you guys ever use GPS to navigate around town, right? That technology would actually not work or not be understood without Einstein's theory of relativity. So that's a fun one. Quantum mechanics gonna close out the year. You know what? That's probably a good pause point right there because I'm out of time anyway. But yeah, you guys know next couple of days we're gonna be constructing this Geneva Drive right here. Get lights, lights. All right, and otherwise, that is our stop point today.